So hello and welcome back to this online machine learning course. In the last video we dealt about classification, which was an introduction to classification. In this video we'll be dealing about logistic regression. So let's move on. In the last video we saw that classification is a process of classifying or categorizing a given set of data points into classes. Today we'll be dealing about logistic regression. Now this is a logistic regression because it involves the logistic function. This is a regression because it involves the regression of probabilities. As I told you in the last video that we map probabilities into our thorough points and we get the output into probabilities. So for example, if this is the class 1 and this is class 2, the probability that the values are in class 1 is perhaps 1 and 0 over here. The probability that it is of class 1 and 2 is perhaps 0.8 and 0.2 over here. The probability that it is of class 2 is perhaps 0.4 and 0.6 over here, and so on. So as you can see, it is a regression of probabilities of these two classes. So basically it is a logistic model. So you should use the probability of certain class or event existing. So yeah, it could be a pass or a fail situation, win-lose situation, alive-dead situation, or healthy or a sick situation. So let's move on further. So how do we actually perform the operations? So now for example, I have got my two tables, right? Now let's say the classic example of perhaps whether to predict whether a tumor is malignant or benign, right? A malignant or a benign tumor. Now my x's or the inputs could be various input parameters such as the size of the tumor, the depth of the tumor, or perhaps the color of the tumor, and so on, the intensity of tumor, the pain of a tumor, and so on. And these could be the values over here. And my predicted output could be a malignant for M or B for benign, right? And I have to predict that whether a new set of features x1, x2 to xn, a new values of the features, what is my new tumor. Now I can actually predict it or solve it using logistic regression. Let's see. So now let's for example consider this to be a malignant class and this to be the benign class, right? Now I express this is a function of 1 by 1 plus e to the power minus z, which is a logistic function, and this z is actually this quantity, right? This is the z quantity out here. And so if I actually, these are x's my inputs, and this is the bias correction, this is the bias term, and this is my z, and when I plug this z over here, I get the respective probabilities of all the classes. And this is how exactly logistic regression works. It is a regression or a continuous value of probabilities. And so yeah, that is how we proceed with linear logistic regression. And for example, the probability that it is malignant would be 1 and 0 over here. For benign, for benign it would be 0 and 1 over here, the probabilities. In this case it would be 0.4 and 0.6 over here. In this case it would be perhaps 0.8 and 0.2 over here. And so we are getting a continuous values of probabilities. Let's move on. So in past few videos we saw about the mean squared error. Now this mean squared error was basically a loss function to actually learn the parameters b0, b1 to b2 to bn. We wanted to learn these parameters through this loss function. And basically we wanted to minimize, because this was the error function. The error has to be minimized. Now, this loss function is also valid in this case. We could easily use this one and get some results, right? But since the probabilities are in the range of 1 and zeros, right? Because all these values range from maximum 1 and zeros. So it is difficult to find it is not a very good approach to solve it with mean squared errors. The better approach is to use a new loss function, and the loss function is known as categorical cross entropy, which is given by this expression. And more formally, we would be using this expression. It is also known as categorical cross entropy. Now, the derivation to this is beyond our scope, and so we won't be discussing that. But whenever we would be dealing with this regression or classification, we would be picking up this loss function only. And so yeah, let's move on further. Okay, so let's consider our two graphs. For example, let me take up this. So for a new data set, I express my z like this and I get to this one, right? So yeah, now let's for example assume z is equal to b0 plus b1 x, right? Now for different values of b0 and b1, and for I will have different, and suppose my equation is 1 by 1 plus e to the power minus z, right? Now for different values of b0s and b1s, I will have different graphs of this function. And for instance, I have got this graph for b0 equal to 0 and b1 equal to 5. This graph for b1 equal to 10 and b0 equal to 0. Now if I keep on increasing my b1 over here, you can see that the graph would ultimately converge or form something like this, right? And you can see it actually forms a threshold function or an ideal threshold function for very large values of b. And so yeah, because so in this case we can have a flexible boundaries in case of sigmoid function, and so it actually proves very useful in various other instances over threshold. And as you can see, we have trained it using the categorical cross entropy loss. And so as for example, you can see how well the dataset actually classifies between these red points and the blue points. The sigmoid function actually perfectly classifies these data points, and also for this cases it actually perfectly classifies these data points. So yeah, so basically here we are dealing with a regression of probabilities, and we are classifying these into two categories, or a binary classification. So yeah, that was for today. Thank you for watching.